Hi everyone, good evening all of you. Today I am going to give a presentation on cathodoluminescence, which is an important analytical technique that gives information about the spatial resolution of electron microscopy. Let's start. These are the contents I will discuss in details, like introduction and importance of CL, transition between valence band and conduction band, instrumentation, comparison between SEM and CL images, angle resolved CL, and CL spectra for undoped and doped aluminum nitride, color cathodoluminescence, advantage and applications of CL imaging. Let's start with introduction of cathodoluminescence. Cathodoluminescence is the process of generating light when electron beam hit a specimen. Basically, cathodoluminescence is an optical and electromagnetic phenomena in which electron impacting a luminescent material cause the emission of photon which may have wavelength in the visible region. Also, cathodoluminescence imaging is an analytical technique that combines functional optical information with the superior spatial resolution of electron microscopy. Why cathodoluminescence is important? It has many applications. Cathodoluminescence emission can be used to explore many fundamental properties of matter. It can be used to study light transport, scattering, structure of materials, electronic structure of materials, including semiconductor like band gap and defects, resonant, resonant phenomena, and much more. Uh, Cathodoluminescence emission refers to the emission of visible light in response to the electron bombardment in the electron microscope. Electron bombardment induces various ionization process and electronic transition induces in non-metallic materials or promotion of electron from valence band to the conduction band. The subsequent return of the electron from the conduction band via direct transition as shown in this figure by 1 and via the trap states showing 2 and 3 is responsible for CL. When electrons are promoted in the conduction band, holes are left behind in the valence band, and the reverse process may be regarded as a radiative recombination of electron hole pairs. CL work best with the insulating or semiconductor materials such as ceramic, organic and biomaterial, since they have a clearly defined band gap, but not with matter because they have not defined band gap. It is also informative for material containing defects or dopants with associative interband trap level, since the wavelength of CL emission are characteristic of the species or defects responsible. CL can be used for both analytical and imaging purpose to identify species responsible for CL emission and map their location in a sample at the nanometer level. CL finds practical application as fluorescent screens in a range of display devices. This is the instrumentation sketch of the CL. The electron beam passing uh, through a small aperture in the parabolic mirror, which collects the light and reflects it into the spectrometer. A charge coupled device and a photomultiplier tube can be used for parallel or monochromatic detection respectively. An electron beam induces current signal may be recorded simultaneously. This is the sketch of cathodoluminescence objective inserted in an SEM column. In SEM, a focused beam of electrons strike on a sample and induces it to emit light that is collected by optical uh, an elliptical mirror. From there, a fiber optic will transfer the light out of the microscope, where it is separated into its components wavelength by a monochromator and is then detected by photomultiplier tube. By scanning the microscope beam in an XY pattern and measuring the light emitted with the beam at each point, a map of the optical activity of the specimen can be obtained. And this figure showing in the right side showing two type of CL microscope are in use. One is working with a cold cathode generating an electron beam by a corona discharge tube, and the other are produces a beam using a hot cathode. Cold cathode CL microscope are the simplest and most economical type, and this hot cathode type generate an electron beam by an electron gun with tungsten filament. The advantage of a hot cathode is the precisely controllable high beam intensity, allowing to stimulate the emission of light. To prevent charging of the sample, the surface must be coated with a conductive layer of gold or carbon. This is usually done by a spectral deposition device or a carbon coater. This figure showing two such spectra are collected on a quartz sample at different excitation positions. Both show characteristic quartz CL peak, but this blue peak is absent in the spectrum. Due to this spark cathodoluminescence system used a photomultiplier tube detector in conjunction with a filter wheel. This allows intensity mapping at seven distinct wavelength bands. The wavelength information can be obtained by using color filter. This figure showing a SEM image on the left and CL measurement on the right. The additional details on the right was acquired using a photomultiplier tube and three filters in the blue and green part of the spectrum. The additional detail revealed with the CL measurement help in determining details of crystal growth, defects and other artifacts of interest. This is the angle resolved CL. In CL imaging, the wavelength dependent intensity is often studied. In addition to the wavelength of the emission, light is also characterized by a wave vector. The momentum and propagation direction of the wave. The direction in which light is emitted contain valuable information like how a nanostructure object emits and scattered light. This figure shows is an experimental example of such a profile measured on a single crystal's gold substrate corrected for mirror geometry. The experiment on the left demonstrates the full beam profile and the correlation with the theoretical example on the right. This example used in SEM to energize the top of a gold nanopillar and measure the angle of the CL radiation coming off from the top of the pillar. In this example, the radiation was toroidal with little CL signal perpendicular or parallel to the top surface. Every point within the profile can be directly associated with the specific emission angle in the upper angular hemisphere from which CL is upper angular hemisphere from which the CL is collected. Such imaging is also known as in optics as Fourier imaging, refer to the fact that one image momentum space rather than real space. The use of CL as a powerful analytical technique, especially when combined with SAM-EDS as shown in the figure for sample of aluminum nitride that were either endoped or doped with 0.2% of europium. The CL spectrum of both sample, this is showing in A, the CL spectrum of both sample shows a peak at 360 nanometer, which is attributed to the defect in the parent structure, whereas spectrum of the doped sample shows an additional weak band at 550 nanometer. As we can see in this figure, this A figure showing CL image using the two spectral peak shown in this B and C using 360 nanometer and 550 nanometer spectral peaks, which may be deduced that the europium is essentially concentrated at the grain boundary regions. This is further confirmed by SAM. This D1 is showing SAM image and EDS image. This E1 showing EDS image of grain and grain boundary region, showing the regions of high europium content in this E showing high europium content. Parts of the EDS spectra in F showing for the two regions showing a high concentration of aluminium in the grains with a much smaller concentration of aluminium in the grain boundary but a high europium concentration. These results collectively shows that europium has a very little solubility in the aluminum nitride crystal lattice. Instead, europium dopant segregates to the grain boundary where it probably forms a separate crystalline phase. Without the high resolution capabilities of SAM, EDS and CL, such information could not be obtained. These are the key advantages of the CL imaging. Using electron as an optical excitation source has a superior resolution in the electron microscopy. CL measurements are performed with an electron microscope environment. Also in CL we can overcome the diffraction limit. They give high excitation resolution in 1 to 10 nanometer range, and CL can be used to correlate nanoscale geometrical features with the optical response. CL has many application areas. It has great applications. Showing application area in material science, CL can be used to study ceramics, dielectric and semiconductor both in bulk and nanostructure material, and to determine their light emitting properties at the nanoscale. And CL can also be used for functional material including scintillator, phosphors and high power electronic light emitting diodes diode lasers and solar cells. Also, CL can be used as a powerful method for studying optical phenomena at the nanoscale. These structures find applications in biosensing, fluorescence enhancement, non-linear optics, low threshold steam generation, LED solar cells, and integrated photonic laser and etc. Also, CL can be applied to metallic as well as dielectric and semiconductor nanostructures. Thank you.